NMR is quite a detailed, lengthy topic that I'm really going to try to condense here in just a few slides to give you the basics. We're going to look at proton NMR. So this is showing us the protons in the molecule, the hydrogen. Every chemically distinct proton in a molecule gives rise to an NMR signal. So if we look at this molecule here, I'm going to work it from right to left. We have a methyl group. That CH3 is one type of proton. There's no hydrogen at the carbonyl carbon. Then we have a CH2 group. That's another type of proton. We have another CH2 group that's a different type of proton. So why aren't the two CH2s equivalent? Well, one is close to a carbonyl, one's close to an isopropyl. They're in different environments. They can be differentiated. Moving on down, we have this CH, which is D, but then that carbon has two methyl groups coming off of it. Those two methyls are attached to the same carbon. They're completely equivalent. So those would both be E. So this molecule here would have 5 proton NMR signals. And then those signals are split by the neighbors. So what that means is you count the number of protons on the neighbor and add 1 to that. So if we work through this one, if we look at this carbon, here's its neighbor. The neighbor has 0 protons. 0 plus 1 is 1. So that is just going to be a single line, which is called a singlet. Okay, now let's look at this carbon, or the protons on that carbon. On its neighbor, there's 2 hydrogen. So we take 2 plus 1 is 3. The signal for that one will be split into 3 lines, or a triplet. So a triplet looks kind of like that. Next, let me redraw this so we're not writing on top of things we've already done. Let's look at the signals for this proton. So you want to look at the neighbors. We have a neighbor here, a neighbor here. The neighbor on the right has 2 hydrogen. The neighbor on the left has 1 hydrogen. So the total number of neighbors is 3. 3 plus 1 is 4. That's a quartet. A quartet looks kind of like that. Okay, now let's look at the hydrogen on this carbon. Right, so here we have neighbor here, here, and here. This would be 3 plus 3 is 6, plus 2 is 8. So 8 neighboring protons, 8 plus 1 is 9. That would be split into 9 lines. 9, we just call that a multiplet. And then finally, we have the signal for the CH3 groups here. You only need to look at one of them to figure this out because they're equivalent, so they give the same signal. So let's say we're looking at these protons on this carbon. Here's the neighbor. The neighbor has 1 hydrogen. 1 plus 1 is 2. That'll split into 2 lines, or a doublet. So a doublet's just kind of like that. So that's the four types of signals that you would see in the NMR spectrum. The next thing you have to consider is, once you know what signals you're going to have, where do they show up? And for Proton NMR, they show up usually in the 0 to 12 parts per million range. And it really depends on the environment that they're in. If they're just regular, sp3 carbons, they usually show up toward the right end of the spectrum, which is called upfield or shielded. So the upfield region of the spectrum, shielded protons. The left end is downfield and deshielded. If the proton is next to a carbon with a double bond, that falls in the allylic region. If it's on a carbon containing a heteroatom like oxygen, nitrogen, or a halogen, that shifts it downfield to about between 2 and 5. If it's directly on a double bond, that's in the vinyl region. If it's on an aromatic ring, it falls in the aromatic region. Then we have aldehydes and carboxylic acids. Alcohols and amines can show up anywhere. And they usually show up as a singlet. Typically, alcohols and amines don't split. So if we want to apply this to our example down here and figure out where these signals go, we need to figure out the different protons involved. So we have protons here, that's type A. Hydrogen here, we'll make that B. CH2C, D. The OH will be E. And monosubstituted aromatic rings often just show up as a multiplet in the aromatic region. So we're going to just draw that as one big chunk, F. So it's all about the environment. A is just a CH3, nothing all that special. So A is going to appear down here in the saturated region. B is on a carbon next to an OH. So that's going to fall in the electronegative region. So let's stick that in there. C is a CH2. It's really not in any predominant region. It might have a little bit of a pull from the OH, but not much. So we're going to put it down there very close to A. There's C. D. D is a CH2, but it's next to this double bond. Because of that, we're going to put it in the allylic region. So I'll put D here. F is the aromatic ring. We'll put that in the 6.5 to 8 region. And then E is the OH. Again, it can show up anywhere. I'm just going to throw it here around 5 because that's a nice open space. Now, it would probably be good practice if you go through and try to assign the multiplicities or the splittings to each of these. I will go ahead and draw in and kind of fill in the spectrum so you would know what it looks like. So here's how the spectrum for this one might look. A, we would expect to be a doublet. B, would be a sextet. C would be a quartet. D would be a triplet. E, which is the OH, I drew that as kind of a broad singlet. And F is this multiplet for 5 hydrogen, which is the aromatic ring. I put the integration numbers above each signal, which tells us how many protons each one corresponds to. So here's an example of how we might work through a proton NMR. In this case, we are given a molecular formula. So the first thing you want to do is figure out the number of unsaturations, which will tell us the number of rings or pi bonds. Use the formula 2 times the number of carbon plus 2 minus the number of hydrogen minus the number of halogens plus the number of nitrogen divided by 2. So in this case, we have 2 times 5 carbons plus 2 minus 12 hydrogen. There's no halogen, no nitrogen, oxygen we ignore. Divide that by 2. So we get 12 minus 12 divided by 2, 0. There's no unsaturations here. So no rings, no double bonds. From here, what you want to do is go through and try to identify fragments on your spectrum. Do that by the number of hydrogens. So the way I would do this, I say, here's a peak for 2 hydrogen. Let's make that a CH2. Here's a peak for 1 hydrogen. Make that a CH. Here's a peak for 1 hydrogen. Make that a CH. 2 hydrogen, CH2. 6 hydrogen. Well, you can't have CH6, so if you see something like this, it's usually 2 equivalent CH3 groups. From there, check your work. See if you have 5 carbons accounted for. 1, 2, 3, 4, 5, 6. I made a mistake. I assigned something as a CH that shouldn't be a CH. What else do we have here? We have an oxygen. So maybe instead of a CH, one of these is an OH. And OHs usually don't split, so I'm not going to do that one. But what I can do is cross that one out and make that an OH. From there, I like to go through and just add dots to show how many bonds each thing needs. For example, the CH2, the carbon has 2 hydrogen. It needs 2 more bonds to be a happy carbon with 4 bonds. The CH needs 3 bonds. The OH needs 1. CH2 needs 2. These methyls each need 1. Now use your splitting to help you out. This is split into 3 lines. N plus 1 is 3. N equals 2. That means the neighbor that that's connected to should have 2 hydrogen on it. Well, we're in luck. There's only one option. The CH2. So that works out. Well, now if we look at this CH2's peak or signal, it's a quartet. N plus 1 is 4. N equals 3. Well, it's already connected to 2 hydrogen by this neighbor, so it must need to be connected to something with 1 hydrogen. OHs usually don't cause splitting, so we're going to connect it to that CH. Then if you look at these CH3s, this is a doublet. N plus 1 is 2. N equals 1. Those CH3s need to be connected to something with one hydrogen. Well, that's going to be this carbon right here. So let's do that. All right, we're only left with a dot here, a dot here. So let's connect those together. We didn't even really use the chemical shifts here, but the reason that this signal is clear down at about 3.6 is because it's connected to the electronegative oxygen. So let's clean up our structure. So we have OH connected to the CH2. That's connected to another CH2. That's connected to the CH. And that's connected to two CH3 groups. So we do that, and we're done.